Today the first speaker I will tell you about Laurent Cortella. He's a physicist, head of facility Arc Nucleart. Arc Nucleart is a consortium of French Commission, Atomic Energy Ministry of Culture in city Grenoble. Okay?
Okay, thank you, ladies and gentlemen. I would like first to thank the organization to give me this opportunity to present our activity of using gamma ray for cultural heritage conservation with such an audience. Okay, next. Actually, I am not a conservator. I am a nuclear physicist, but dealing with conservation of cultural heritage for more than 20 years. I am working in a small structure called Arc Nuclear. It is located in the middle of a big research center of the French Commission for Atomic Energy, the CEA, in Grenoble, France, the biggest city of French Alps. This activity arose more than 50 years ago from the idea of using nuclear techniques for heritage conservation. The first treatment that was done was the consolidation of an inlet parquet, historical inlet parquet in 1970. Then many artifacts, mainly from the surrounding of the city, were treated. But what definitively launched the activity was the fungicidal treatment of the Ramses II, the second mummy in 1977. And I will speak about that later. Today, Arc Nuclear has a special status of public interest consortium. It is supported by the CEA, which is the first provider, but also by the Ministry of Culture and by the city of Grenoble. And it is now also a collaborating center of the IAEA, the United Nations Agency for Atomic Energy, a collaborating center dedicated to cultural heritage conservation. Arc Nuclear is both a workshop and a laboratory. A workshop providing service for conservation with three specialties: biocidal treatment of many different kinds of collection, conservation restoration of archaeological waterlogged organic materials, and conservation restoration of wooden polychrome sculpture. And it's also a laboratory making research to improve the technique for conservation, when, for instance, also to face new problems, and valuing our resource and skill also in the field of research and development in other fields. And we have a special, we have also a small activity of characterization of cultural heritage by analytical techniques. It is important to say that all those activities can use or not gamma irradiation. It is not mandatory. And finally, we have a mission of dissemination. That's what I am doing today. To conduct those activities, we are a small multidisciplinary team, 20 people, including technologists and scientists, but also conservators and even a curator made available by the Ministry of Culture. We operate 3,000 square meters of facilities, including, for instance, large-scale freeze dryer, and impregnation, large-scale also impregnation tanks. And our more specific facility is still a gamma irradiator. So I won't give a physics lesson, but I just want to give some keys about gamma rays. Gamma radiation is light. It is carried by a particle called a photon, just like visible light, but the difference is that the energy of a single gamma photon is about 1 million times that of visible light, and 10 to 100 times that of common X-ray, which is another kind of light. Such energetic photons come from radioactive nucleus. You know that the mass of matter is mainly inside the nucleus of atoms, and as mass is energy, changes in the nucleus can generate high energy radiation, the so-called nuclear radiation. When it interacts with matter, gamma photon can eject electrons from the atoms, that is, it ionizes some of them. Of course, it can't generate radioactivity because it can't interact with the nucleus and destabilize it in unstable radioactive nucleus. This is totally impossible. As its probability of interaction with matter is relatively low, gamma photon can penetrate deeply even in dense matter, unlike other radiation like beta or alpha, which will stop after few distance in the matter. Typically, attenuation is only a factor 2 after 10 centimeter of water or plastic, or after 1 centimeter of lead. And of course, everybody knows gamma rays are dangerous, I think so, and produce biological effects. This is because ionization in molecules involved in life can cause biologic effects, of course. And according to those, it can cause damage on cells and even the death of the affected organism. Let's turn now to process of cultural heritage conservation. More precisely, let's focus on remedial conservation, which is, according ICOMCC, all action that directly applied to an item or a group of items, and with the objective to arrest current damaging processes or to reinforce their structure. With my words, these are just treatments that directly apply to the item to stabilize it. So, what to do with gamma irradiation? First, arresting damaging biodeterioration using biocidal effect of gamma rays against pests. Second, reinforcing items by radiocurable resin. So you can understand that we are exactly in the scope of this remedial conservation. To achieve those treatments, our tool is a cobalt-60 pool irradiator. We use industrial seal source distributed on a source rack 1.6 meter large and 0.9 meter high, just like if it was neon tube, but emitting gamma light instead of visible light. To protect us from radiation, the source rack is stored under water with at least 2 meters of water shielding the radiation. The pool on the side of the irradiation chamber is a kind of bunker with 1.5 meters concrete wall. Once the artifacts settle inside the irradiation chamber, after going outside and closing the door, which is also 1.5 meters concrete, around 6 tons, the source rack can be winched for pulling it up from the pool and irradiating the artifact, which can be on both sides of it. So now, treatments. First evident application is biocidal treatment to fight against biodeterioration. Main pests are insects and fungi, including rots, molds. Some of them are able to make disappear a piece of softwood in few years. The idea is just a simple exposure to radiation of the whole volume of the artifact in order to kill those pests. It is just a matter of dose. For insect, we are looking for to reach deterministic death, whatever the species and whatever the life stage. We need at least 500 gray, which is already around 100 times that of the lethal dose for human by deterministic effect. So it's very huge doses. For fungi, we have no more deterministic effects, but probabilistic ones. With common fungi infestation like molds and rots, for instance, 5 kilogray is enough to kill at least about 99.99% of the initial population. On the other hand, the important point is to be sure that radiation will not affect the material property, and once again, it's just a matter of dose. We have a big knowledge about the possible effects which were studied in many fields, and of course, many investigations were done for cultural heritage, not only in our laboratory, but in many laboratories in the world. First concern is about color of transparent material that can darken and tint because of activation of color center after trapping of electronic excitation. This is the only real contraindication. Other phenomena like cross-linking, chain scission, and radio-oxidation are very low, under 10 kilogray. Basically, we can measure some few effects at the molecular scale, but this never had effect at the macroscopic scale. So, how do we proceed? There is, for instance, an irradiation of a Japanese palanquin in lacquer wood with metal decoration. The artifact is put inside the irradiation chamber at the right place to get the right dose rate. Then we close the door and pull up the source rack. Here, it is what you can see in chamber during the irradiation. You can see the source rack. You can see the tube. These are the source. And in the other side, it is the palanquin. We have to turn the object at mid-irradiation in order to have a good homogeneity of the dose in the whole volume of the artifact. Of course, we are sure to cross all the artifacts because we can calculate easily the dose rate and we can measure the dose with dosimeter on both sides of the artifact. So it is very, very reliable. This is very important. From 50 years, we have treated thousands of collections, meaning tens of thousands of artifacts, furniture, wooden sculpture, also because we have this specialty of conservation restoration, painting, ethnological artifact, musical instrument, natural history specimen, books and archive, modern art, and also some unusual collection like frozen baby mammals or mummies. Let me show some example of treatment. Here, insect eradication of private collection of furniture. We, of course, treated many thousands of objects from surrounding ethnological museum with, for instance, many sleds, bobsleds, and ski from our mountain region. but also many historical objects from museum or castles, like this sedan chair from 18th century, before its restoration by our conservators. And at least I will say 1,000 of polychrome wooden sculpture coming from church. Indeed, in our workshop, irradiation is always the first step before restoration, as this is our preventive policy to avoid any cross contamination between different sculpture. Only after the irradiation take place the restoration. Here are some examples in which restoration included release of polychromies. In the first example, with this Pieta from the 14th century, there were different layers with different color, with some inappropriate restoration with plaster, so that it was decided to turn to the first original layer, even if it was known that by previous polychromy study that it was largely incomplete. The second is a Mary Magdalene sculpture from 17th century that was repainted in white plaster done in the 19th century, as it was often done at that time. And our conservators therefore released the up layers and restored the underlying colors. Another example is here with this Pentic removal of this nice Christ on the cross sculpture from 16th century that was previously covered with recent and thick and heavy paints. We were surprised to find the four evangelists in the cross, as we initially supposed that the cross was not the original one, all painted in black, but instead it was the original one. We treated also a lot of modern art that is often said relatively perishable. Perishable often means that it is biodegradable, with many different kind of materials. Something quite new in France, but common in some countries like Brazil, Romania, is the decontamination of archive and books. In 2016, facing a big disaster due to water leaks after a building disorder, the French National Archive asked us to treat 11 linear kilometers of different documents on other archive. In this case, because of the presence of some poorly studied material for their behavior under irradiation, we make some emergency research to verify that their behavior under irradiation was not a problem prior to irradiate them. For instance, there were paper tracing, blueprints, and it was okay. So we can treat it, all this archive massively. And from time to time, we have a very uncommon customer, like baby mammals, that we treated at bactericidal doses for sanitary reason, but which in turn helped to its conservation. And also some mummies, the most famous one being, of course, the one of Ramses II, which was treated 46 years ago for fungi concerns. We have always to face some new issues, like here some cases with the rescue of an Egyptian mummy that was frozen after a flood in order to avoid the growth of fungi. After this irradiation, we were able to thaw and dry it by freeze drying. We also treated recently the burial of a medieval abbot with humid organic remains, both for sanitary reasons and for its conservation, awaiting authorization for laboratory study. We have to maintain it in humid state to conserve it because also there were some textile, and if we dry the textile, it was then impossible to unfold them. Something also interesting is the disinfestation of a Gallo-Roman wooden ex voto released by the melting of an alpine glacier. I didn't say for all this treatment, but what you can see on those pictures is that more often we treated the artifact inside their packaging, which is almost transparent to the gamma rays, avoiding difficult manipulation and danger for the artifact. Okay, let's talk now about our second technique of remedial conservation using gamma ray. It's the consolidation with radiocurable resin. When we developed this technique in the 70s, we call it the nucleart method. It is a consolidation by densification in two steps. In the first one, the microporosity of the artifact have to be filled with the resin by a vacuum pressure impregnation process. And then we make it harden by the ionizing effect of gamma rays. The resin we use is styrene, unsaturated polyester, and thanks to ionization, we induce cross-linking of the resin that stay and still fill the wall microporosity thanks to capillarity force. So the quantity of consolidant is maximum, as there is no evaporation step. All the liquid is transformed to solid. It is very different from usual consolidation, which use solvent and evaporation of solvent. So you've got only a film of consolidant inside the microporosity. So this is really very efficient, but it is also very invasive. The artifact become heavier, the color may darken and enhance to some extent due to wetting effects. And above all, it is absolutely irreversible. It is very stable, of course, but it is absolutely irreversible. And this is contrary to the ethics of conservation. So we use this technique only in some justified cases. It can be the last chance technique when conventional techniques are not able to meet the conservation issues, or when a powerful mechanical reinforcement is needed to conserve functionality of the artifact, like in the case of parquet floor, for instance, on which you want to still walk on. It can also be justified in some cases of treatment of archaeological wood, taking advantage of the very good mechanical and chemical stability of the hardened resin with comparison to other techniques. Here is the case of an extremely weakened polychrome wooden sculpture that was attacked by xylophagus insects, as you can see. Before complete consolidation, our conservator tried to clean and fix what was possible to do with conventional techniques. Then the different pieces were impregnated with resin in a vacuum pressure tank, and finally irradiated to solidify the inside resin that stay in the microporosity. So that it was possible for the conservator to reassemble and to do again classical restoration with structural filling, fine putty, color retouching, support, before it could be exhibited again. I would like now to talk about the specific case of waterlogged archaeological wood. Being surrounded by water is the main way organic materials escape from total biodeterioration when artifacts are left abandoned. But what remains, having the good shape, is no more real wood. Cellulose is slowly leached after biological degradation due to anaerobic bacteria and hydrolysis. It is so that wood cannot support drying. It will collapse due to capillarity forces when the water withdraws from the porosity. To avoid that, the conventional technique use polyethylene glycol, said PEG, to reinforce the cell wall, and freeze drying to avoid capillarity force during the drying. It is the conventional technique used all around the world, and this is also the main technique we use in our workshop for waterlogged wood. However, in some cases, because treatment with PEG is not very stable from mechanical and chemical point of view, we modify the treatment using less PEG and completing the treatment with radiocurable resin. It is what we call the mixed nuclear treatment. And I will finish this presentation with the most impressive work from my point of view we done 10 years ago for a Gallo-Roman boat that was found almost complete in the Rhone River in the city of Arles in south of France. It was 31 meters long, 3 meters large. The shipwreck asked for to be removed from the river after cutting it in 10 sections, as it was impossible to remove it in a single element. Our conservator started their work directly on the side of the river, dismantling all the different pieces they could before to transport them to our workshop in Grenoble to be treated. This is the pro, which was the last section removed from the river. As you can see, it was reinforced by iron plates. And it was an issue because it can't be dismantled, and we knew that due to the hydrophilic nature of PEG, conventional treatment will enhance corrosion problems. Furthermore, the confirmed presence of sulfur would have led to formation of pyrite and sulfuric acid. All pieces were treated first with impregnation of PEG before to be freeze-dried. However, here you can see the pro elements and the mast, which were impregnated with minimum of PEG, just enough to be dried without damages. At this point, it was possible to clean the pro from material that were attached to iron plates, and after that, to impregnate the remaining porosity with styrene polyester. Here you can see the pro inside a modern wood frame to make it more easy to manipulate. Now cleaning the excess of resin of the surface before to finally cure the resin thanks to irradiation. And then, after this conservation treatment, came the restoration with the hard work for supporting the boat, you can imagine, 31 meters long. And prior to its final assembly in the museum, with here some of the last elements before the pro, and final adjustment of the position of the pro, and here is the boat in exhibition after reassembly. I must mention that also the mass was treated with the nuclear method, not for chemical stability, but in order to reinforce it enough to be presented in vertical position, which was not possible if using only PEG. So I hope you agree that gamma irradiation is an interesting tool for conservation, and thank you for your attention.
Very specific, but very interesting presentation. Thank you. Are there any questions from the audience? Yes.
Do you have any plans on doing a project with the Latvian Restoration Society?
Yes.
Sweet. That's all.
Any more? I have a question. Maybe I missed that, but what about health questions for restorers that are working after with these objects?
It is very important to understand that when you irradiate with gamma ray, or with X-ray, or with electron, you can't generate any radioactivity. Just like light. You turn the light off, no more light. Okay? It's really simple. Those radiation are unable to make nuclear reaction. So they are unable to destabilize the nucleus. And radioactivity is just when a nucleus is not stable. So it's not that it's minor. It's completely, totally impossible. With that kind of radiation, some other radiation like alpha, like neutron, will generate radioactivity. So no issue about radiation.
Okay, thank you. Okay, thank you.